Have you ever thought about how strange the cost of air travel is? Normally, if you want to get someplace faster, it's more expensive. But if you want to save money, maybe go a little bit slower, maybe you just handle it yourself. For ground travel, this is how it works. Like suppose, for example, you wanted to go between San Francisco and Los Angeles. You want to get there as fast as possible, but to stay on the ground for whatever reason. If cost is no object, the fastest option would be high-speed rail. Well, okay, maybe that's a bad example. Suppose you wanted to go between Paris and Lyon. You want to get there as fast as possible, but you want to stay on the ground. The fastest ground option is going to be high-speed rail, the TGV. That will run you about €100 and it will take a little under 2 hours. Now suppose you don't have much to spend. If you're willing to go more slowly, you can save money. There aren't actually many slow trains these days between Paris and Lyon, but if you can find one, it should be cheaper. Or you can take the bus. Again, pretty slow, lower tech, so of course it's cheaper. €20, about 80% off. Or, if you're willing to DIY it and you own a car, you could just drive yourself. Lower tech than the TGV, the driver's unpaid, it's just you, and all you're paying for really is gas and wear and tear on your car. If you do that and you carpool, you can cut the cost down again by about 80%. This all makes sense. Different modalities, train, car, bus, they're all in the same ballpark in terms of price, and the faster options cost more. Now let's go back to California and suppose that we want to travel between San Francisco and LA, but do it by air. If you're flying commercial, you can get an economy ticket for around $100, and the flight time will be about an hour. We'll ignore the time spent in the TSA lines and commuting to the airport and all that because that's more of a social issue than a technical issue. Flight time of an hour, that's pretty fast, but suppose we want to save some money. Are there any other options? What would be the equivalent of driving your own car? I guess if you owned a Cessna, maybe a 172, had your pilot's license, and could fly yourself and some friends, that would be the equivalent of driving your own car. How do the expenses compare? Well, turns out you don't actually save any money. Despite the fact that you don't have to pay for a pilot or flight attendants, and the trip takes much longer, you save nothing. What about switching modalities? What if we change the type of vehicle, like when we change from a train to a bus? Well, the only other option I can even think of would be a helicopter. I've never heard of anybody doing this, but it's theoretically possible. But with normal hourly operating costs and helicopter speeds, you're probably looking at least 20 times as much as the cost of a commercial flight. So this doesn't really make any sense, right? In almost every way, the commercial jet is better, and it also manages to be cheaper. So rich and poor, almost everybody chooses this option. A lot of decisions, when you dig down, are driven by money. But then if you dig down even further, the reason something is cheaper or more expensive is because of some nuance of physics. And so it is in this case. These prices have a lot to do with the physics of lifting bodies like wings and helicopter rotors. And so today, we're going to dig into the physics of the wing. I want to start out by mentioning the explanation that I was given for why a wing produces lift when I was younger. You see, it has to do with the shape of the wing. This teardrop shape, this wing shape, the top surface is longer than the bottom surface. So if an air molecule goes along the top surface, it has further to travel than a corresponding molecule traversing the bottom surface. So it's obligated to move more quickly to bring the streams together at the trailing edge of the wing. There's a law of fluid motion called Bernoulli's law, which is basically just a way of writing down the conservation of energy. We have a term for the work done by the flow, which is proportional to pressure, a term for the kinetic energy of the flow, and a term for the gravitational potential energy of the flow. Now, gases aren't very dense, so unless you're talking about thousands of meters of difference in height, this third term doesn't really matter much. So typically we just worry about the first two terms. So you can see here this adds up to a constant, which means that the flow velocity speeds up, the pressure has to go down to compensate. So when we look back at the wing, we know that the flow on top is faster, so that means the pressure on the top surface of the wing is lower. So because of this, there's a net force on the wing, which lifts it up. This is a terrible explanation. First off, why the heck would it be true that two molecules that split up are obligated to reach the trailing edge at the same time? Are they like coordinating with walkie-talkies? There's no particular reason that the upper surface being longer means that the fluid has to flow faster. I mean, if that were the case, then something like this would make a really, really good wing, right? This has a super long upper surface, so those molecules would really need to rush to make it to the back of the wing in time. And this has been experimentally tested, and in reality there's no synchronization of the flow. The paths of the two molecules might look something like this, where they arrive at the trailing edge at slightly different times. Now it is true that on average the airflow is faster on the upper surface of the wing, and so it's also true that via Bernoulli's law the pressure is in fact lower. But that's due to some very complicated reasons that we'll talk about later. It is most certainly not due to telepathic nitrogen molecules. To understand this a little better, let's simplify the problem. The whole point of a wing is to produce lift, an upward force. If that force is equal to the weight of your airplane, then great, you'll cruise along straight and level. If it's less, you fall out of the sky, and if it's more, then you climb. Now the wing will also produce drag, and drag is bad. Drag is a force pointing backwards, tending to slow the plane down. You have to counteract that with thrust, which comes from the engines, which burn fuel, which costs money. So more drag means more expensive. So let's try to figure out what our options are to maximize lift and minimize drag. Let's just forget about complex fluid flows for a moment, and let's just model the wing as a tilted board. And we'll model air as a series of ping pong balls hitting that board. A cubic meter of air weighs about 1 kilogram, so we'll just treat that air like it's packaged up in discrete balls rather than as a fluid. That makes things easy. We can't really get much simpler than that. The balls bounce off the board and they change their momentum. That means that there will be an impulse in the opposite direction on the board. If the balls are striking the board at some regular cadence, we'll have a change in momentum per unit time, which is just a force. That force will be perpendicular to the board. And if we take the components of that vector, then voila, we've got lift and drag. So now let's see what happens as we change the tilt of the board, and here's where we start to get some insight. The maximum lift is at 45 degrees. If we go beyond that, lift goes down and drag goes up. So definitely want to avoid that. But maximizing lift isn't really what we want. Instead, what we want to do is maximize the ratio of lift to drag. And so notice as we make the angle of attack even smaller, lift goes down, but drag goes down even more quickly. As you approach zero, we get to an undefined limit because both the lift and the drag are going to be zero. But we can see that as we approach it, the ratio starts to go up to infinity. So you are most efficient when the angle of attack is zero, but unfortunately, at that angle, you also produce zero lift. Now you can immediately see some ways in which this model is not realistic. For example, the ball is going to lose some energy when it bounces off. It's going to lose some velocity. And so this vector is going to get smaller, which makes the force on the board change direction. And basically you end up with more drag and less lift. And in this scenario, the best ratio for lift to drag is now some very small angle, where there is some non-zero lift and some non-zero drag. But assuming you don't lose a massive amount of energy with the bounce, assuming that the ping pong ball isn't coated in molasses or something like that, it's going to be a pretty small angle and a pretty small amount of lift. So the takeaway from all this is that the wing is creating lift by changing the flow direction, and that creates both lift and drag. And the efficient way to get lift is to only change the flow direction by a tiny, tiny amount. Now we don't use rectangular boards like this for wings, and the reason is because airflows are different than volleys of ping pong balls. Molecules in one part of the fluid interact with molecules in other parts, unlike ping pong balls. And this board shape doesn't play well with fluids. You tend to get eddies forming along the leading edge, which really mess up the flow. This is the equivalent of coating the ping pong ball in molasses. So what we need is a shape that will smoothly redirect the flow without causing any drama. And guess what shape works really well for that? The wing shape. You can't really deduce that the wing shape is what you need from first principles. And in fact, the optimum shape is highly dependent on the details of the flow. The ambient pressure, density, velocity, viscosity of the fluid, all of these things will dictate what shapes work well. Now here's where we can see that in the earlier explanation, there was a grain of truth buried in a bunch of magical thinking. The wing redirects flow down, so there must be a reactive force on the wing. But how is that force actually transmitted? The only way a fluid interacts with the wing is by applying a pressure to it on all surfaces. So the only way that it can apply a net force on the wing would be to have a pressure differential on the top and bottom surfaces. The pressure has to be lower on top for lift to occur. So if the pressure is lower on top, then by Bernoulli's equation, you simply have to have a higher local fluid velocity on the top of the wing. Coming at this from Bernoulli's equation versus looking at momentum changes of the airstream are just two different lines of attack. It's like problems from Physics 101. For example, if you throw a coin off a tower, how fast is it going when it hits the ground? Well, you could figure out how much potential energy it has and assume that all that gets converted to kinetic energy, and then calculate the velocity at the ground. Or you could apply the acceleration of gravity to the falling object and calculate its final speed based on kinematic equations. Two totally different approaches, but you'll get the same answer either way. It's a similar idea here. But while it's pretty easy to calculate the speed of a coin using either strategy, calculating lift from Bernoulli's equation is hard because you have to solve for the velocity of the fluid flow everywhere. And that velocity is governed by the Navier-Stokes equation, which is a complex equation. And anyway, if this equation doesn't look like enough of a bear, know that for many situations, it doesn't even have an analytic solution. You just have to let computers approximate the answer. Now that stuff has its place, but it's kind of against the ethos of the Napkin Engineering channel, obviously. Okay, so let's apply what we found out to real-world problems. We know we need to create a certain amount of lift. We know that we create lift by accelerating air downward. We give it momentum downward, so we can either accelerate a small mass of air to a high velocity or a large mass of air to low velocity. They just need to multiply to the same value because momentum equals mass times velocity. We know that the second option is a better choice than the first option, large mass, low velocity. We learned that from our ping pong ball model, but we probably didn't even need that. For example, if I accelerate a mass of air downward, my force will be proportional to the momentum change, mv. The momentum that the air gets is mv, but the energy that it gets is 1/2 mv squared. That energy has to come from somewhere, and indirectly it comes from the plane. So you have to counteract this by burning gas in the engines to create thrust, which again costs money. So suppose you have some mass of air and some velocity, and suppose you double the mass and cut the velocity in half. The lift stays the same. The kinetic energy imparted to the air goes down by half. Mass doubles, the v squared term goes down by a fourth, so the net effect is half as much energy you've got to pay for. Let's think first about a helicopter. The rotor spins, air is accelerated down, and the mass of air is approximately going to be proportional to the size of this circle. If we want to up the velocity, we spin the rotor faster, but that's not efficient. Instead, we want to increase the mass of air, so we've got to make the rotor larger and the area of this circle larger. But this creates a bunch of problems on its own. Longer rotor blades are more stressed and need to be beefier to not snap. Another problem is that the tips are going to go way, way faster than the rotor at the hub. The tips may get close to supersonic velocities while the hub is barely moving. So that can cause all kinds of problems and inefficiencies. Another approach, instead of making a bigger rotor, is to just have more rotors. You'll notice that large helicopters usually have 2 rotors rather than one enormous rotor, so at a certain scale, this is the preferred solution. But this is not a great approach either, because more engines means more complexity, more points of failure, and multiple small engines are usually a lot less efficient than one big engine. So this isn't great either, and it's just hard to make helicopters efficient. They're just stuck in the rut of accelerating smaller amounts of air by a large velocity, which is inherently inefficient. Now, that's not as bad as like a jetpack, for example, but it's not good. A helicopter is more efficient than a jetpack, but really neither of them are terribly efficient. Now let's think about airplanes. Consider that Cessna 172. As it travels forward, it interacts with a certain volume of air, and that's going to be proportional to this rectangle. So say we want to make it more efficient by making the volume of air greater. We can just make the wingspan larger. This will help out, but it does create the same set of problems that we saw with the helicopter. Really, really long wings like that are fragile. But there's an easy solution. Instead of making the wings long, just keep the wings normal length and fly fast. This jet sweeps out the same area per unit time as the Cessna with super long wings did. But it does it with narrower wings and fast travel instead of long wings and slow travel. And so now you can see why commercial airliners are so cheap. It's actually more efficient to fly high and fly fast than to fly low and slow. Within limits, of course. Once you start getting towards the speed of sound, things get really inefficient really fast. But there's a sweet spot that commercial airliners take advantage of to everybody's benefit. As much as I like to complain about air travel, it is pretty crazy to think that I can just hop on a jet for a few days' salary and be almost anywhere in the world. Thank the clever engineers.